Hey there. Going to try something new for this lesson on 7.5 parametric equations. So here we go. Let's see, you're going to have to bear with me. I'm trying something new. Here, let's see. All right, here's our notes. With parametric equations, if we were in person in class, I would have started with this group activity before I even taught you anything about it. This little discovery activity gives you a good idea of what exactly parametric equations are and how it works, basically. All right, so we're going to jump into this activity. I'm going to work our way through a couple of them with you. The first one we have: Anytown High School is planning a play. The script calls for two characters to meet on stage. Lauren starts at the point 0 feet, 6 feet, and travels horizontally at a rate of 1 foot per second. Alex, however, starts at the point 4 feet, 0 feet, and travels vertically at a rate of 2 feet per second. If Alex and Lauren start walking at the same time, will they meet? All right, so on part A, we're going to use the grid that's here to graph the walk. So first, Lauren. Lauren starts at 0, 6 feet. All right, so that's right up here. And she travels horizontally at a rate of 1 foot per second. So after 1 foot or 1 second, she's gone 1 foot. Another second, she's gone another foot, and so on. So then we can see Lauren, her path looks like that. Alex, however, starts at 4 feet, 0 feet, and he travels vertically at 2 feet per second. So vertically, he goes 2 feet for every second. So there, 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 and there. That is the path for each of them. So now on part B, from the graph in part A, can we determine if Alex and Lauren meet? Well, if I'm just looking at the graph, it kind of looks like they do, right? Because we see there is a point of intersection, but did they cross it at the same exact time? So in this case, no, they don't meet. Because they reached that point at different times. All right, if we look at it, we can see it took Lauren how many seconds to get to that intersection point? 1, 2, 3, 4. It took Lauren 4 seconds. Now let's look at Alex. How many seconds did it take Alex to get there? 1, 2, 3. So Alex got to that intersection point quicker than Lauren did. And so he had already been through that intersection point by the time Lauren had arrived there. So based off of what we've just seen, we're going to complete the table of values for both Lauren and Alex. So when time is 0, Lauren started at a position of 0, 6. After 1 second, she then moved 1 foot, so 1, 6. At 2 seconds, she moved another foot, so 2, 6, and then 3, 6, 4, 6, 5, 6, 6, 6, and 7, 6. Now at the very last line of this table, how does my X column, how do those values compare to my T column? Well, they're the exact same. So then at the very bottom, it's T. Now let's look at my Y values. Well, my Y values remained constant the entire time, and that's a value of 6. So now let's look at Alex. Okay, so Alex started at a horizontal position of 4 and a vertical position of 0. For every second, however, he moved 2 feet. So vertically, after 0, he jumped up 2 feet, so 2, and then 2 more feet, 4, 6, 8, 10, 12, 14. Horizontally, the X position of 4, he stayed at 4 the entire time. So this time, as we look at what happened with all of our X values, well, those remained constant the entire time at a constant value of 4. Now let's look at the Y values. How do the Y values relate to time? Well, we have time 0, Y vertical 0, 1, 2, 2, 4, 3, 6, 4, 8. So what do we notice about these values for Y? It looks like they're double whatever the time is. So if it's double the time, that is 2t. So then part D, down below. Can you tell from the table if Lauren and Alex meet? Okay, do they have the same point of intersection? Yes, they do. 4, 6, 4, 6. But notice the time. It took Alex 3 seconds, whereas it took Lauren 4 seconds. So yes, we can show. So yes, the table shows they don't meet. And again, they reached the same point of intersection, but it happened at different times. So now part E. We need to write a pair of equations for Lauren's horizontal and vertical position in terms of the third variable or parameter, which is time. These are called parametric equations. So parametric equations come in pairs. They're divided up between an x sub t equation and a y sub t equation. The x equation always deals with the horizontal position of the object at any time t. The y equation always deals with the vertical position of the object at any time t. So for Lauren, we can get her set of parametric equations by the bottom line in our table of values. X sub t equals t, y sub t equals 6. And that's what we showed in the last line of our table. All right, so part F. We now need to write a pair of equations for Alex. And this will show Alex's horizontal and vertical positions in terms of the third variable time. So for Alex, if we go back and look at that table, we can see his horizontal equation is 4 and his vertical equation is 2t. So as we go back over here, for Alex, x sub t equals 4 and y sub t equals 2t. All right, so it looks like parametric equations are a set of equations with both an x equals and a y equals equation. They always come in pairs. And again, the x equation gives the horizontal position of an object at time t, and the y equation gives the vertical position of an object at time t. Using the pictures below, input all of the settings into your calculator and press graph to see the visual representation of the actor's paths. The 3 variables in a pair of parametric equations can represent anything, but in this particular problem, X and Y represent positions, and T represents time. So first, go to mode on your calculator. And from mode, you're going to go 4 down. Normally, our calculator mode is in function mode. But what I want you to instead do is arrow to the right, PAR. PAR is parametric mode, so press enter on PAR. Go 2 below that and arrow over to SIMUL, which stands for simultaneous mode, and make sure you press enter on that. When you put the calculator into parametric mode, when you go to your window settings, it now looks like this: X sub t, Y sub t. And it happens first set of equations, second set of equations, and so forth. So for Lauren, X equals t, Y equals 6. And for Alex, X equals 4, Y equals 2t. All right, in your window settings, we have what's called a T-min and a T-max. So right now, I just want you to set that at 0, 6, and a T-step at 0.1. X-min 0, X-max 6, X-scale 1. Y-min 0, Y-max. There's nothing there, but I want you to put in 10. And let's see, Y-scale 1. Looks like the window got a little messed up there, but those are the values that I want you to put in. Okay, I'm going to pause the video and I want you to enter that into your calculator and press graph. Okay, so what you should have noticed is it went really fast. Okay, so what would cause it to go that fast? It's actually your T-step. So now I want you to go back to your window and change your T-step only, but this time change it to 0.01, and then graph it again. Okay, I'm gonna pause the video, graph it. All right, so you should see the effect that this had, it slowed down the graph. So the T-step slows down the graph. What happens is your T-step is telling the calculator how many points to plot between the T minimum and the T maximum. So when we had T min 0, T max 6 with a T-step of 0.1, think about how many points that's plotting. When I put in a T-step of 0.01, well, now it's plotting a lot more points. And so when it's plotting a lot more points, it slows the graph down and it takes longer to do it. Okay, so letter G. The script for this play was incorrect since Alex and Lauren do not meet on stage at the same time. The director of the play decides that Lauren and Alex should meet after 4 seconds. So we need to write a new pair of parametric equations that will produce this result. Well, we can actually leave Alex's equations exactly the same. X equals 4, Y equals 2t. Lauren. Her equations, however, we need to change. So if we go back and look at her table of values, I need her to be able to be in the same position as Alex at 4 seconds. So at 4 seconds, Alex is at the position 4, 8. So what do I need to change on Lauren for her to be at 4, 8? Well, the X value is where we want it. So that's T. But the Y value, do we want it to be 6? No. What do we want the Y value to be? 8. So what we're going to do is for Lauren, oops. X equals t, but y equals 8. So instead of her having the horizontal line at 6, we're moving her up so she has a horizontal at 8. And now the two of them will meet at 4 seconds. All right, let's try another one. A bug is crawling up a wall. He starts at the bottom left corner of the wall. He's crawling along the wall 2 inches to the right every second and 1 inch up every second. A lizard is 6 inches above the floor on the left corner of the wall. He is traveling a ½ inch down for every second and 2 inches to the right every second. So part A, the graph to the right shows the paths of the lizard and the bug. From the graph, can you determine if the lizard and the bug meet? Well, if we just look at the graph, it appears maybe they do because there's an intersection point. But just looking at the graph, can we actually determine if they're crossing at the same exact time? And the answer is no. Just looking at the graph doesn't show us about the third variable, time. All right, so now let's actually plot our points. Let's see, it says the bug starts bottom left corner of the wall. Okay, so here. And he goes 2 inches to the right and 1 inch up every second. So 2 over and 1 up, 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 over 2 up 1, over 2 up 1. How many seconds did it take the bug to get to that point of intersection? 1, 2, 3, 4. Now the lizard. Lizard starts 6 inches above the floor on the left corner of the wall, here. And the lizard goes down ½ of an inch and 2 inches to the right every second. So down half over 2, down half over 2, and continuing throughout. So lizard, 1, 2, 3, 4. It took the lizard 4 seconds to get to the same intersection point. So did they actually meet? Yes, they did. Filling in the table on part B, the bug. Horizontally, the bug went 2 feet for every second, or 2 inches, excuse me. So 0, 2, 4, 6, 8, 10, 12, 14. In terms of time, what happened? Well, when time was 1, horizontally it was at 2. Time 2, horizontally 4. So it looks like the x values were all doubled from the time. So that would be 2t. Vertically. Vertically, the bug went up 1 inch for every second. So it started at 0 and then went up 1, 2, 3, 4, 5, 6, 7. Well, you can see all of your y values and all of your time values are exactly the same. So at the very bottom of the y column is t. Now the lizard, right? The lizard went to the right 2 inches every second. So that's horizontally, started at 0, 2, 4, 6, 8, 10, 12, 14. So he would be 2t horizontally. Vertically, however, he started up at 6 and went down ½ of an inch every second. So from 6, he went down to 5.5, and then 5, 4.5, 4, 3.5, 3, 2.5. Oops, sorry about that. Plane went overhead. But it's too nice outside. Had to feel the great outdoors. For this equation, all right, for y, we have to see how it relates to time t. Well, we start at a y-intercept of 6, and we're subtracting half an inch, so minus 0.5 for every second t. So 6 minus 0.5 t. Part C, from the table of values in Part B, can you determine if the bug and the lizard meet? Do they share the same point of intersection? Yes, they do. 8, 4, 8, 4. How much time did it take each of them to reach that point? 4 seconds. So yes, we can tell based off of the table, when do they meet? At t equals 4. And what is their position when they meet? That's at 8, 4. So part E, what variable can you see in the table of values in part B that's hidden in the graph in part A? We can see time, t. That is clearly shown in the table. Okay, so part F, write a pair of equations for the bug's position in terms of the third variable or the parameter time. Well, we saw for the bug, at the bottom of the table, x equals 2t and y equals t. Part G, write a pair of equations for the lizard's position in terms of the third variable or parameter time. Well, lizard had x equals 2t and y equals 6 minus 0.5t. So now part H, use your calculator to graph the parametric equations that you wrote in parts F and G. I want you to pause the video now, go to your calculator, type in those equations, set your window settings, and then come back. And when we come back, we're going to complete the table of values below. All right, in our table of values, the x value for the bug was 0, 2, 4, 6, 8, 10. The y value went 0, 1, 2, 3, 4, 5. Well, this time, what I want to do is I want to write a y equation that's in terms of x. So look at your x column, 0, 2, 4, 6, 8, 10. Now look at your y column, 0, 1, 2, 3, 4, 5. How do your y values relate to your x values? So we can see all the y values are half of every x value. So then our equation here would be 0.5x. For lizard, my x values were 2, 0, 2, 4, 6, 8, 10. And my y vertical values, 6, 5.5, 5, 4.5, 4, 3.5. This time when I write the y equation in terms of x, well, we have a little bit of work to do. We know what our y-intercept is, but I need the slope. In order to find the slope, pick any 2 points, y2 minus y1 divided by x2 minus x1. So if I picked my y-intercept and the next whole point, y2 is 5 minus y1 is 6, divided by x2 is 4, minus x1 is 0. Well, we end up with a slope of negative 1/4. So if I write that equation, it's negative 1/4 x plus my y-intercept of 6. So part I, write a position function for the vertical distance y in terms of the horizontal distance x for the position of the bug. That's what we did there. So y equals 0.5x. Letter J, write a position function for the vertical distance y in terms of the horizontal distance x for the position of the lizard. Y equals negative 1/4 x plus 6. K. Write new parametric equations so that the bug will travel the same path, but he will pass the point where his path crosses the lizard's path after the lizard. Use your calculator to check your answer. Okay, so now bug needs to cross that same path after the lizard. So what we need to change is T. I need to slow him down. So if I'm going to slow him down, I need to take time away from the bug. So if I'm taking time away, then the x equation. Instead of the x equation being x equals 2t, let's take 1 second away from time. So 2 times t minus 1. The y equation, well, instead of y equals t, how much time did I take away? I took away 1 second. So instead of y equals t, it's going to be y equals t minus 1. So now on L, will the parametric equations you wrote in part K change the position function that you wrote in part I? Explain your answer. Well, did I change the position function? No. He still travels the same exact path, but what did I change? I changed the time in which he travels the path. So the answer is no. The bug travels the same path, but 1 second later. All right. So just as with the Lauren Alex theater stage problem or the bug lizard problem, just seeing a graph of their path does not tell us the whole story. We don't know if the pairs ever intersected each other unless we look at the third variable. So rather than having a relationship with y defined as a function of x or x defined as a function of y, we have both variables defined as functions of a third variable, which is the parameter. And right now that is time. So our next example, example 3, we might have a function defined this way. X equals 2t, y equals t squared plus 1. From this, we could construct a table of values to determine the graph or path of the function in the xy coordinate plane. So we have t values in our table, 0, 1, 2, 3, 4. So 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. X is defined as 2t. Y is defined as t squared plus 1. So we start by plugging a t value of 0 in for both of those equations. So if I plug 0 in for t there, then I have 2 times 0 is 0. If I plug 0 into t squared plus 1, then I have 0 squared plus 1 is 1. Then we move to t equals 1. Plugging it in for the x equation, 2 times 1 is 2. Plug it in for t squared plus 1, we would have 1 squared plus 1. 1 squared is 1 plus 1 is 2. Taking the value of 2 and plugging it in, 2 times 2 is 4. But for the y value, 2 squared plus 1 is 5. Taking t equals 3. 2 times 3 is 6. 3 squared plus 1, 3 squared is 9 plus 1, gives us 10. And last is 4. 2 times 4 gives us 8 for x. And then 4 squared plus 1 gives us 17 for y. Now we're going to graph it. As we graph it, we start with our first point when t equals 0, and our point is 0, 1. Our second point is the point 2, 2. Let's see. So over 2, up 2. Notice the x-axis goes in increments of 1s, but the y-axis goes in increments of 2s. So be careful on that. The next point is 4, 5. The next point is 6, 10. And then 8, 17. So now between those points, connect them. But do not draw beyond that last point, or do not draw prior to the beginning point, because it's showing the position of an object at any given time. So when functions defined parametrically are graphed, we're able to restrict how much of the function we want to see by restricting the parameter. So if we restrict the function defined above for what we did, t is between 0 and 4, we can graph that part of the curve above. But it doesn't exist beyond that because that's what we defined it for. Also, when we graph functions parametrically, we put arrows on the graph to indicate the direction of flow of the graph. So our starting point was 0, 1, and our ending point was 8, 17. So our object is moving on the path in that direction. So we need to put arrows going in that direction. Example 4, sketch the curve given by the pair of parametric equations over the given interval. Make a table of values. X equals t squared minus 4, y equals 3t minus 8, for t values between -5 and +5. So that's what we start with, our t values. -5, -3, -1, 0, 1, 3, 5. Notice I did not do every single one. I skipped around, or skipped them, but I kept it somewhat consistent. I didn't have to fill up the entire table of values. I left the last one blank because this will give me enough points to see clearly what we're doing. My x equation was t squared minus 4, and the y equation was 3t minus 8. We're going to pause the video now, and I want you to fill out your table of values. All right, your x values you should have gotten. -5 quantity squared minus 4 gives us 21. -3 squared minus 4 is 5. When we plug in -1, we get -3. Plugging in 0, we get -4. Plugging in 1, we get -3. Plugging in 3, we get 5. And plugging in 5, we get 21. Notice what happened to those values. They repeated themselves, all right? 3t minus 8, plugging in -5 gives us -23. The next one was -17, -11, -8. And again, that would be 3 times 0 minus 8 gives us -8. 3 times 1 minus 8 gives us -5. 3 times 3 minus 1, or minus 8 gives us 1. And 3 times 5 minus 8 gives us 7. Plotting these points. We start with the point 21, -23. So over 21, down -23. 5, -17. -3, -11. -4, -8. -3, -5. 5, 1, and 21, 7. Connecting our points. We only connect those points. We don't go anywhere beyond that because it is defined from t greater than or equal to -5, but less than or equal to +5. Now we show with arrows the position the object is traveling along this curve. We started down below and we worked our way until we finished at the point 21, 7. All right, last bit. You can convert your parametric equations to rectangular equations and vice versa. So parametric, an x equation and a y equation in terms of t. Rectangular equations are functions y defined by x. So we can go back and forth in between parametric and rectangular. To do this, you need to eliminate the parameter. So example 5, write x equals negative 3t and y equals t squared plus 2 in rectangular form. So right now we're given the parametric equations. We need to change it so it's an xy equation only. To do that, look at each of your parts of your parametric equation. Which equation would be easiest to solve for t? Well, that would be the x equation. So on the x equation, I solve it for t. So that is t equals negative x over 3. Once we have that value from t from one of our equations, we're now going to plug that in for t in the other equation. So y equals, instead of t, I plug in negative x over 3. That value is squared plus 2. Simplifying it, negative squared becomes positive. X squared over 3 squared is 9 plus 2. That is the rectangular equation. What kind of graph would that rectangular equation be? Well, when you see the squared, that means it is a parabola. So you can see a set of parametric equations that give us a parabola. Part B, without worrying about domain restrictions, write x equals 1 over square root of t and y equals t plus 1 divided by t in rectangular form. Okay, again, we're going to take the easier of those two equations, x and y, the easier one to solve for t, and that's probably going to be the x equation again. So when we take x equals 1 over square root of t and we solve it for t, we're going to have x times square root of t equals 1, divide by x, and then square both sides. So t equals 1 over x, quantity squared. So t equals 1 over x squared. We now take our value for t and plug it in for t in our y equation. So y equals 1 over x squared plus 1 divided by 1 over x squared. Simplifying this, anytime I divide by a fraction, that means we multiply by the reciprocal. So when we multiply by the reciprocal and distribute that throughout, 1 over x squared times x squared is 1, plus 1 times x squared is x squared. That is our rectangular equation for that set of parametrics. And once again, that is a parabola. Example 6. This one's a little bit different. We need to convert x equals 2 times cosine theta and y equals 4 times sine theta to rectangular form. If your parameter is theta, where theta is our angle measure. Okay, so let's look at this. X equals 2 cosine theta. If I solve that for cosine theta, then I have cosine of theta equals x over 2. Y equals 4 times sine theta. If I solve it for sine of theta equals y over 4. Now, we have something, you're going to love it. We have something that connects sine and cosine. Think the big three. And with the big three, Pythagorean identities, remember? Sine squared plus cosine squared equals 1. Hey, you thought you were done with it. Nope. So in place of sine squared of theta, we're going to plug in y over 4. So y over 4 squared, because it has to be squared, plus cosine squared theta, well, our value for cosine is x over 2 squared equals 1. Simplifying that, I end up with y squared over 16 plus x squared over 4 equals 1. Uh-oh. Do you recognize what that equation looks like? That would be and ellipse. Woohoo! Conic sections are back. All right, we are down to example 7. Use each parameter to write the parametric equations that can represent y equals x squared minus 4. Now, it gives us the parameter that it wants us to use for t. So on the first one, t equals x. Well, whatever you're given for t, you need to solve it for x. Okay, well, that makes this easy. If t equals x, then that means x equals t. Now, since x equals t, in this equation, anywhere you see an x, plug in what x equals. So y equals t squared minus 4. There's your set of parametric equations. Remember, every set of parametric equations has to have an x equals and a y equals. So once you solve the parameter for x, that is your x equals equation portion of the parametrics. The last one, t equals 4x plus 1. Solving it for x, we're going to subtract 1 and divide by 4. So x equals t minus 1 divided by 4. Now for the y equation, we're going to plug that value for x into the equation. So y equals t minus 1 over 4 squared minus 4. Cleaning that up a bit, y equals t minus 1 squared over 16 minus 4. So we come down here. X equals t minus 1 over 4. Y equals t minus 1 squared over 16 minus 4. That represents our set of parametric equations. All right, guys, that is it. Yay! We survived the lesson. And it looks like this worked. Hopefully, fingers crossed that the video actually recorded. Anyway, I miss you guys. I hope y'all are doing great. Please reach out to me. Email me, text me. Let me know how you're doing. All right.